I am Karla Morris. Today I will present the work entitled Formal Verification of Front-to-Completion Style Statecharts using Event-B. This work is the result of an ongoing collaboration between Sandia National Laboratories and the University of Southampton. The outline of this presentation is as follows. First, I will provide an introduction, which includes a motivation behind the use of statecharts, as well as a brief background on SCXML, Event-B, UML-B, and Run to Completion, which are the modeling languages and the semantics that we use to support our modeling and formal verification approach. We will then illustrate a model construction using this incremental design approach, which relies on the use of refinement. In the next section, we will discuss some of the types of properties or requirements we are required to verify, and in the last section, we will summarize our conclusions and future work. Let's start with the introduction section. Graphical languages have always been attractive to engineers, that is, things like statecharts or state machines. And this is something that we can see from the popularity of tools like MATLAB in the case of Simulink and Stateflow, or ANSYS tools. These tools allow engineers to concretely represent their design and in some cases use simulations to explore the capabilities or functionalities of the design. However, their support for formal verification of the model properties is limited or non-existent. There are other tools like Rodin or Event-B that enable the use of formal proofs for their model properties. These tools support the idea of abstraction and refinement, where in each refinement level the engineer is allowed to add complexity to the model by making the implementation details increasingly more concrete. There are many definitions of refinement in the literature. We are interested in a refinement that preserves safety properties. Our goal is to get the best of both worlds. We take advantage of the graphical nature of the statecharts, and we want to also explore the power of formal verification provided by Rodin. In order to be able to introduce refinement to statecharts, we have to impose some constraints to the statecharts. In particular, statechart transitions cannot cross the state containment boundaries arbitrarily. Statechart XML or SCXML is a modeling language based on Harold statecharts. SCXML is a textual representation of the statechart, like the one shown in the bottom of this slide. XML follows a run-to-completion semantics, that is, that we have the idea of trigger events that may enable transitions within these statecharts. These trigger events are added to a queue whenever a trigger is raised by the system. A trigger event is the queue and consumed by firing all the transitions that it enables. After the trigger is consumed, all enable and trigger transitions, that is, transitions that do not have a trigger in their conditions, are taken until there are none left. At that point, we are ready to dequeue a new trigger. There are two types of trigger events. There are internal triggers, which are the triggers that are raised by the model, and there are external triggers, which are raised by the environment. For our purposes, these triggers are raised non-deterministically. Internal triggers have a higher priority than the external triggers. That is, that the internal trigger queue has to be empty in order for us to dequeue an external trigger. Event-B is the language used by Rodin, the tool which gives us the modeling and formal verification framework. Event-B provides us with a formal methods for system design, and it relies heavily on refinement. Event-B models have two parts. One are the context that contains the set, constants, and axioms associated with the models, and two, the machines, which holds the variables, the invariants, and events in the system. The machines and the context are refined. Refinement is the process by which the engineer adds implementation details to the model. There are basic rules of refinement. One is the superposition refinement, which includes adding auxiliary variables to the model. These new variables are used to define guards and actions that capture the new functionality added to the model at a particular refinement level. Two is data refinement, where we replace abstract variables, that is, variables that were present in the abstraction, with new concrete variables that capture some of the more concrete behavior in the model. Three is the new event refinement. Each machine in the Event-B model has an implicit skip event that does nothing. This abstract event skip can be refined by new events in the refined machines, and these new events will add the new functionality of the model. The tab listing is an illustration of an abstract model. It has an event E, which is the abstract event, which has a guard and actions associated with the V variable, the abstract variable. The bottom listing illustrates a refinement of that machine, where we have a refined event F that refines the abstract event E. We have added a new concrete variable W, which allows us to define guards and actions based on that new variable. UML-B is the diagrammatic modeling notation for event B. It allows us to construct our models graphically. UML-B does not support the run to completion semantic. This is something that we're superimposing as part of this work. There is no idea of triggers in UML-B. All the transitions are on trigger transitions. The type diagram is a UML-B state machine. Here E is the name of the event that the transition from S1 to S2 denotes. There are two states encoding supported by UML-B, Boolean variables and enumerated types. In the work that we present here, we use the Boolean variables encoding. There are different forms of refinement supported. One is the superposition refinement, where we add a new state machine within an existing state. Two is the guard strengthening, where we add auxiliary variables to express new guards, which are predicates or conditions that must be satisfied for the transitions to be enabled. And three is the new events, which can be, for example, explicit transitions, self-transitions added to the model. The listing that we show here corresponds to the event B encoding of this state machine. Each transition in the state machine corresponds to an event B event in the listing. We use the Boolean variable encoding for the state, so we have this additional invariant that stipulates that at most one state can be true at the time. The run to completion semantics is implemented by a specified abstract basis that is extended by every model that we construct. The basis consists of an event B context and an event B machine. The context holds the sets for all the triggers that you have in the model, as well as the internal and external triggers. The basis have the variables for the internal queue triggers, the external queue triggers, the run to completion, and the dequeuing, and all the events that are associated with the run to completion. This is a state chart-like representation of the run to completion semantics. At initialization, the UC completion flag is false. The internal and external trigger queues are both empty, and there is no trigger to be dequeued. The T is empty. Next, if no triggers and trigger transitions are enabled, we fire the completion event to set the completion flag to be true. Let's say that at that point, some of the non-deterministic events associated with raising the external trigger are fired. Now, since the internal trigger queue is empty, we can proceed to dequeue that external trigger. Next, the future trigger transitions events will fire, which will fire all transitions that are enabled by that trigger and potentially raise internal triggers as well. The next step is to fire all untriggered transitions, and again, some of those transitions may actually raise internal triggers. When no untriggered transitions are enabled, we fire the completion event. Then we proceed to dequeue one of the internal triggers. If no transitions are enabled by that internal trigger, we take the no trigger enabled transition event and start over. The next section is the model construction section. In this section, we follow a set of refinement rules to enable the incremental design process. One, the nesting rule, which allows us to embed a state machine within an existing state. We can add OR states or parallel states as shown. Two is the guard strengthening rule, where we refine by adding guards or conditions to existing transitions. For example, the abstract transition from state SA to SB can be refined by adding the child SD to its guard. Three is the action strengthening rule, where we can take an abstract machine like the one shown here and add auxiliary variables to add conditions and actions to the transitions. These rules are the ones that we follow in our approach. There are many different definitions of refinement. Sirani et al. Uses another set of rules within their Science of Computing programming journal. Sirani's rule 2 and 3 are similar to our nesting rules. Rule 7, the state extension rule, and Rule 8, the bad refinement rules, are rules that we do not support. Even though these rules preserve the state reachability given a provided input, they do not. They also allow for behavior in the refinement that may not be present in the abstraction. Now, these rules allow the constructions of models that can potentially violate the preservation of safety properties, which are of interest to us. To illustrate the ideas of refinement, we will use this quadrature helicopter model. The first abstraction model will be the stature on the tab left, where we provide basic functionality for the drone. How is it that it goes from an off state when it sees a external trigger on, it proceeds to a start, and then to the operational state that will take care of all the takeoff, flying, and landing capabilities. There is a set of external triggers being on, takeoff, and off, and a set of internal triggers to fly, to land, and land it. At this point in the refinement, all these triggers are fired non-deterministically. This first refinement level we achieve by applying the nesting rule, and we provide additional details by refining the takeoff state. Here we remove some determinism from the model by explicitly adding a transition that raises the internal trigger to fly. The second refinement level of the drone introduces a parallel state to capture the functionality related to the battery. Here we have a battery OK state that monitors that the battery is above a certain threshold. Whenever the battery hits the desired threshold, we migrate to a battery low state and we fire a to land trigger to initiate a landing sequence. One requirement that will be relevant for this level of refinement is the fact that we want to ensure that for the battery OK state, the charge remains above a specific threshold. The third refinement level associated with this drone, we introduce new refinement to the climb state by introducing these two climb to and abort states. Here we are removing some of the non-determinism again by explicitly raising the to land trigger, and we are adding additional behavior to guard the allowable values for the battery charge. One property that will be of interest at this refinement level is to ensure that if takeoff is true, that implies that the battery is okay, or that you have a to land action following that because you don't have enough power to operate the drone. The next section is the model verification section. We are interested in verifying and preserving safety properties in our system. We can use the theorem prover within the Rodin tool to prove these properties. An example of a requirement for a safety property is the controller should not continue to the takeoff or fly state if the battery charge drops below a specified threshold. We can write this property ideally as if the battery OK state is true, that implies that the charge is greater than 20%. Now, a consequence of that property is the invariant that tells us that if we are in that takeoff state, this takeoff state equals true, that implies that the battery is okay. That means that we have enough charge to perform our takeoff capabilities. Now, these properties, as written, will not be satisfied by our reactive system. We have to keep in mind that we do not have a perfect synchronization between the time that the triggers are raised and the time that those triggers are consumed by the system. To be able to account for that, we need to look at the properties at the completion of the macro steps. In the case of the battery okay state, where that is true, that implies that either I have a charge greater than 20 or I'm still in the process of completing the macro step. In the case of the takeoff state, it's either the case that I am in the battery okay state or I have a to land trigger in the internal trigger queue or ready to be dequeued. We may also be interested in improving liveness properties. For this, we use the LTL model checker Pro B. An example of this property is the battery charge should decrease its value after an external trigger event decrease charge. The idea of representation for this property will take this form where it will be globally true that if the external trigger event decrease charge is enabled, that would imply that eventually the current value for charge will be less than the previous value. Now, this property fails to model check, and the reasons for it is the model construction and the fact that we have a reactive system. So we revise this property to account for the reaction of the system. First, we want to account for the fact that we only monitor the charge within the battery okay state. So we want to make sure that we have the predicate that says that we are in battery okay state, and we have that particular constraints on the charge. Next, we want to revise this to account for the fact that we actually have other triggers in the external triggers in the queue. So we, for example, want to make sure that we don't have that off trigger in the ready to be the queue or in the external trigger. Because in that case, we will not observe that decrease in charge, or we will just power off the drone. The final section of this presentation is conclusions and future work. During this presentation, we demonstrated the use of the refinement principles applied to a reactive state chart and how we translate that state chart to event B for verification. The rules of refinement that are used are such that we are able to preserve safety properties in the form of invariant properties, which are proven using the Rodin theorem prover. Because we are talking about a reactive system, we have to ensure that the properties are written such that they are whole or evaluated after the reaction is completed. We also demonstrated the use of the LTL model checker to verify liveness properties. Here we want to verify that the system behaves as expected when reacting to environmental triggers. Our future work includes the use of previously developed techniques to enable the verification of liveness properties through the use of the Rodin theorem prover instead of the LTL model checker. We also want to extend the capabilities of the tool to enable automatic execution of the run to completion in the way of an animation. And lastly, we will want to write up the formalization of the semantics for the extended SCXML notation and the refinement rules. This concludes my presentation. At this point, I will be happy to take any questions from the audience.